Okay, welcome to this lecture on the computer organization and architecture subject. This lecture we will be discussing problems and solutions for the questions asked in this subject, computer architecture, in the previous year GATE exam, that is GATE 2023. We will discuss 5 questions that were given in this exam. So let's quickly go over the mark distribution. The mark distribution consisted of 2 1-mark questions and 3 2 marks questions. If you ask my take, not much questions were asked from this subject, but that does not guarantee you that they won't ask many in the next gate as well. It could be that they ask you more questions as well. In this gate exam, it was only 5 questions, but probably more than that can be asked as well, right? So that is what I wanted to say here. So now, without any further ado, let's start with the first question. Okay, so first question is based on the topic pipelining. It says, consider a three-stage pipeline processor having a delay of 10 nanoseconds, 20 nanoseconds, and 14 nanoseconds for the first, second, and the third stages respectively. Right? And assume that there is no other delay and the processor does not suffer from any pipeline hazards. Also assume that one instruction is fetched every clock cycle. The total execution time for executing 100 instructions on this processor is how much nanoseconds? So it's a very simple question. This one is a very simple question. So let's discuss the solution. So focus on 3 things that is given here. One is 3-stage, right? And assume there is no other delay. So there is no other delay. And the processor does not suffer from any pipeline hazards, which means your CPI of the pipeline is always 1. Right? You will never have hazards, you will never have stalls, you don't have the pipeline waiting for any instruction to complete, or you don't have any structural hazard, any data hazard, nothing you have. That's the assumption. You have a 3-stage pipeline, and the delays of these individual 3-stage pipelines are 10 nanoseconds, 20 nanoseconds, and 14 nanoseconds, right? So the time it takes for each stage is given, right? So what I can do is, so before I go into this question, right, let's think of a simple example, okay? So all of you have seen a car manufacturing unit, right? First, there will be one stage that will create the body of the car, right? Let's say the body of the car takes 2 days, okay? And let's say after the body is made, the wheels are attached, okay? So if wheels are attached, let's say it takes 1 day to do it. And then the final stage, let's say it is painting and finishing. Painting and finishing, which takes, let's say, 15 days. So if you see, the stage that takes the most amount of time is the painting and the finishing stage, right? So let's say I want to make one car, okay? And let's say this is stage 1, this is stage 2, this is stage 3. One car first goes through stage 1, takes 1 day, plus it goes to stage 2. Sorry, take 2 days because stage 1 is 2 days, I said. Sorry. So it takes 2 days, stage 2 takes 1 day, and then stage 3 takes 15 days. So in total, I take about 18 days to create one car, right? Now, if I would have to create 100 cars, if each car was taking 18 days, 100 cars will take 1800 days, right? Simple. Okay. So should this be the answer? No, because there is another word written, pipelined processor. Okay. Now, what is the concept of pipelining? So pipelining would mean, so I hope you all understood this. Let me erase this out. Okay. Let's keep the stages intact. Okay. So let's say this was car 1. Okay. It came, you are making car 1. It went to stage 1. Then it went to stage 2. Then it went to stage 3. This is at T1. This is at T2. This is at T3. Okay. When car 2 is supposed to, let's say you are also making another car 2, C2 in this case, one thing that you can do is after the first car has been completely made, which is S3 is done, you will start making S car 2. Other thing, if you notice, look at time T2. At time T2, car 1 is currently in the stage 2, which is the wheels are being attached. So can't I just create the body of car 1, car 2? The car 1 body has already been created at T1. It is now the wheels are being attached in T2. Can't car 2, can you create the body of car 2 then? You can, right? And after this, once car 1 is doing the painting and finishing at time T3, the unit that handles attaching the wheels is now free. So you can send car 2 there. And then car 2 comes out in T4. Okay. Let's say car 3. You're trying to make car 3. At time T3, you can see that, yeah, orange. So at time T3, you can see the body unit is free, right? Because car 1 is now doing the painting and finishing. Car 2 is now currently doing the wheels attached. So car 3 will do the body, then it will do the wheels attached, and then it will do the painting and finishing. So at T5. So can you see one pattern here? The pattern is car 1 took three T's, right? T1, T2, T3. But car 2 only took 1 T. Car 3 only took 1 T. So this is not called T actually. In computer science term, this is called a cycle. Okay, clock cycle. So let me write this as clock cycle. In the sense, let me write this as C1, C2, C3. Okay. Don't be confused, guys. Okay. C1, C2, C3. Just imagine a cycle as a unit of time where you can do some work. So if you see, after every cycle, a new car is coming out. At C6, C4 can come. Sorry. Oh, okay. Might sound again confusion. So I hope you get the point, right? So this is nothing but car 1, car 2, car 3, and the column is clock cycle. At C6, another car will come out. C7, another car will come out. C8, another car will come out. C9, another car will come out. So if you see every clock cycle, there is one car coming out. That is why the ideal case pipeline CPI will be always 1. What is CPI? Cycles per instruction. So these are instructions. These individual cars are instructions. Instruction goes through 3 set of stages, S1, S2, S3. And cycles taken per instruction in the long run is 1. Why in the long run? Because look at car 1. It is still taking the 3 clock cycles like the non-pipeline case. But every subsequent car is taking only 1 clock cycle. Now, if you have understood this, then the other thing that you have to know is these are cycles, right? We need to talk in terms of time, right? How much time it will take you per stage, right? So what I can do here is, see, so let's use a different color. Let's use gray. So S1 took 2 days, S2 took 1 day, S3 took 15 days, right? What I can do is, I can say that, see, I have 3 options, okay? Let's take the 3 options. Either I can put my cycle time, this is, let's say, time per cycle, as either 2 days or 1 day, or I can put this as 15 days. Let's analyze each of them. If I make the cycle time as 2 days, okay? If I ask you, can you complete all stages in 2 days? Your answer will be no, because S3 is taking 15 days, right? So if I fix this cycle time as 2 days, S1 will finish, S2 will finish, but S3 will not finish. It will be incomplete. It has to take 15 days. So you can't take cycle time as 2 days. Now, if you take the cycle time as a minimum, which is 1 day, that is also a disaster, right? Because if you take the cycle time as 1 day, then the body stage is taking 2 days. You're not even able to finish the body, right? You will have half body finished of a car, and then you know what happens later. So in the safest bet, what computer hardware, computer systems do is they take the max, which is 15 days. Okay, fine. So if you understood this, then now the question is very straightforward. First, you have to find the time per cycle, which we call, let's say, TP, time in the pipeline case. First stage takes 10 nanosecond, second stage takes 20 nanosecond, third stage takes 14 nanosecond. What is the maximum? 20 nanosecond. So 20 nanosecond is my cycle time, which means if I take 20 nanosecond, I can guarantee you that I can finish any stage possible. You can take more than 20 as well if you want to, but there's no point of taking it because the maximum amount of time taken by each stage is 20 nanoseconds. Okay, fine. So 20 nanoseconds. And then now you have to find out, to execute 100 instructions, what is the total time taken in nanoseconds. Okay, fine. So the time answer, right, is nothing but the acha. Now see here, the first instruction took 3 cycles, right? First instruction took 3 cycles. So this is only for the first instruction. It took 3 cycles into 20 nanoseconds. The remaining 99 instructions will come out in only 1 clock cycle. Okay, so I can write this as 3 plus 99 times 20 nanosecond. So if you love formulas, then formula is nothing but, if it is a k stage pipeline, k plus n minus 1 into tp. I just took 20 as common, right? If you look. So if you now calculate this, you will get the answer, which is, if I just put it in the calculator, it is 2040 nanosecond. Okay, see, there are solutions available that are solving this question as well. My objective is not to solve, but also to help you understand, right? So, hope you understand the concept presented here. Okay, let's move on to the next question. Okay. Yeah. Okay, it's a big question, but let's read together. Yeah. So a keyboard is connected to a computer, is used at a rate of 1 keystroke per second. The computer system polls the keyboard every 10 milliseconds to check for a keystroke and consumes 100 microseconds for each poll. Okay. If it is determined after polling that a key has been pressed, the system consumes an additional 200 microseconds to process the keystroke. Let T1 denote the fraction of a second spent in polling and processing a keystroke. Okay. In an alternative implementation, the system uses interrupts raised instead of polling. An interrupt is raised for every keystroke. It takes a total of 1 millisecond for servicing an interrupt and processing a keystroke. Let T2 denote the fraction of seconds spent in servicing an interrupt and processing a keystroke. The ratio T1 by T2 is rounded off to 1 decimal place. See, first understand the concept. Okay. There is a computer. This is your CPU. Okay. And here is your keyboard. Okay, they are connected by a wire. Okay, some wire they are connected with, USB keyboard or PS2 keyboard, whatever you call it. There are two methods here. First, let's look at T1. Let's focus on T1, which is polling mechanism, which was happening in the earlier scenarios. What happened was, a CPU is executing some instruction. CPU doesn't know what the keyboard is doing. Okay, What the CPU will do is CPU will ask the keyboard that, hey, do you have something for me? Do you want me to do something? Is the user typing something so that I can take it? So it will try to poll. It will try to ask the CPU, ask the keyboard that, hey, do you have something? It will send a signal. Do you have something? And keyboard will say no, right? It's like, for example, if I have given you some work to do, one mechanism that I can do is I can ask you every 1 hour, hey, have you done the work? Have you finished it? Have you finished it? Can you give it? It's like that, right? So that's what it is saying. It is saying that every 10 millisecond, the CPU is doing one poll, sending one request. So now you see the issue, right? If I'm doing some work, I'm asking you every 1 hour that, hey, have you done? Have you done? Have you done? I am wasting cycle, right? I am asking you every time, every 1 hour. So I am wasting my time, right? To ask you always. So that's a disadvantage of polling, but that's what polling is. So 10 millisecond is nothing but. So you need to calculate in just a second, guys. Um, in this should work. Yeah. So in 1 second, right? In 1 second, you will do 100 polls if you calculate. Okay. Again, I'm not doing the calculation, guys. Calculation is not even important. You can leave it here also. Main is to know, understand what it is. Okay. So every second, the CPU is doing 100 times polling. Like if one poll is taking 10 milliseconds, then in 1 second, CPU is doing 100 polls. Okay. Fine. And while it is doing the polling, it is consuming 100 microseconds. Okay. It is consuming 100 microseconds. So total polling time is 100 times 100 microsecond, which is 10,000 microseconds. Okay. And another 200 microsecond is used. So, see, if it is determined after polling that a key has been pressed, so after the CPU asks the keyboard that, have you pressed a key? Keyboard is saying, keyboard is saying, yes, 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 actually the user has pressed a key. The system will consume an additional 200 microsecond to process the keystroke, to process what the user has pressed. So total time taken by the CPU is nothing but, okay, plus 200 microsecond. Understood, right? So this is nothing but 10.2 millisecond. So let me just rearrange it, bring it to the top. I need some space, right? So, okay. So now let's focus on T2. Okay. Now you might ask me that, hey, the keyboard, didn't you consider this thing at all? The keyboard is connected to a computer and is used at a rate of one keystroke per second, right? One keystroke per second. Didn't I move everything to a second? Right? 10 milliseconds taken by one poll, 1 second is taken 100 polls, and that is the rate at which the keyboard is also occurring. That's why I brought the rate to the same level. I brought it to 1 second. So now this 200 microsecond is to process one keystroke. Okay, fine. Huh. Alternatively, what I can do is, let's say I bring back that example. I have given you some work to do. I will tell you, see, I won't bug you. I won't ask you every 1 hour or something. Whenever you are done, you let me know. Whenever you are done, you let me know. Okay. So whenever you are done, you let me know. That is called interrupt. So now the CPU doesn't have to go and ask. Once the keyboard gets a keystroke, that, hey, CPU, I have got a keystroke. Whatever you are doing, please stop for now, address my keystroke, and then go ahead. Okay. So T2 is saying the system uses interrupts instead of polling. An interrupt is raised. So whenever you press a key, an interrupt is raised. It takes a total of 1 millisecond for servicing an interrupt and processing a keystroke. Let T2 denote the time. So T2 is nothing but 1 millisecond. See the difference, right? So what is the ratio of, right, T1 by T2 is 10.2 millisecond. So this ratio is, sorry, not millisecond, guys, sorry. So minutes will cancel out, right? So 10.2, okay, rounded off to one decimal place, which will be the right answer. Okay, see why I'm not doing, why didn't I do a lot of calculation? It says once a keyboard has raised an interrupt, it takes 1 millisecond for the CPU to service that interrupt and process the keystroke. So that's all it has written. Okay, fine. Let's move on to the next question. A 4 kilobyte byte addressable memory is, just a second, guys. Okay. 4 kilobyte byte addressable memory is realized using four 1 KB blocks. Okay, using four 1 KB memory blocks. Two input address lines IA4 and IA3 are connected to the chip select port of these memory blocks through a decoder as shown. The remaining 10 input address lines from IA11 to IA0 are connected to the address port of these blocks. Okay, the chip select is active high. Okay, okay. So I hope you guys know what a decoder does, right? It's very simple. So it's like there are four outputs, right? In this case, it's a 2 by 4 decoder. So four outputs denoting each decimal number, let's say 0, 0, 1, 0, 1, 2, and 3. So whichever, so you know, if I ask you what is a binary of 2, you will say that, hey, Aditya, what I have to do is maybe A4 and A3 are there, IA4 and IA3. You set this as 1, 0, this is 2, and then this line will be activated. This line will go high, and then this chip select will be activated, and so this is called active high. Okay, you might, if I ask you that, hey, you want to activate this line, right, which is the fourth memory block, you will say, hey, IA4 and IA3 should be 1, 1, and that's how I can do that, right? So now they are asking that um, uh, uh, there are, okay, the next line, the input memory addresses I11 to IA0 in decimal for the starting locations address of 0 of each block is indicated by x1, x2, x3, x4 in the figure. So you have to find the starting address, right? So how do you do that? Okay. So let's write the address space first. Okay. Let's write the address space first. So everyone knows what is a 2 by 4 decoder, right? Now 2 by 4 decoder. So let me again write it here, or let's do it later on. Okay, let's first write the okay, 1 second, this has some issue. Yeah, okay, fine. So let's write the address lines: IA11, IA10, IA9, 7, 6, 4, 3, 2, 1, and 0. Okay, fine. Now just focus on the decoder. For the decoder part, you need IA4 and IA3. So others all can be 0. So let me put others as 0. Since there are 4, I won't put anything for IA4 and IA3. Others I can put as 0. Since there are 4 such different x1, x2, x3, x4, so let's write 4. Okay. Okay. Now let's calculate for x1. Where is x1? X1 is in the first memory chip. To activate that memory chip, you need to activate the line Q0. To activate the line Q0, you can tell me that, hey, why don't you put both as zeros? This is X1. Okay. For X2, X2 is belonging to the second chip. For that, you have to activate this line, which is Q1. So you can say 0, 1. For X3, it is the next chip, and for X4, it's the next chip, which is 1 0 and 1 1. So this is 0, this is 8, right? Binary. This is 16, right? This is 8, and this is 24. 16 plus 8, right? So do we have an option 0 at 16, 24? Absolutely. Option C is the correct answer. Okay, fine. So consider a IEEE single. So this question is again now based on IEEE floating point representation, right? And they are asking that consider the IEEE 754 floating point representation where P is A and Q is A. Which of the following represents the corresponding product of these two numbers, again represented in the IEEE 754 reference format? So this is a bit theoretical question because you will have to understand the format of the IEEE 754 representation. Okay, so let's start. So the IEEE, let's look at the single precision format, right? So let's use a color. So this is the format. Okay, you have a sign, you have a biased exponent, okay, and you have a mantissa. Okay, how I remembered, I called it, I wrote this, and then I used to say 1823. Okay, 1823. So 1823. Okay, now first let's convert P. So P is 0x C180000. Okay, C1850. If you just map it to the one that is written on the top, what you can do is you can write this as, so C is nothing but 12 1 1 0 0, 1 is 0 0 0 1, 8 is 1 0 0 0, and then it's all zeros. So this is my sign, so it's a negative number. Okay, the next 8 bits, so 1 2 3 4 5 6 7 8 till here denotes my exponent, biased exponent, right? It denotes my biased exponent. So this is nothing but wait a second. So this is nothing but 131, I guess. 131, and then 1 second. So okay, and then there is all zeros. So mantissa is all zeros. Okay. Now this is implicit normalized. So single precision is implicitly normalized, right? There's no explicit normalization, which means the number is actually 1.0 multiplied by 2 to the power exponent minus the bias. So it's nothing but 2 to the power 4 negative. Why negative? Because it's 1, right? 1 means negative. Okay, fine. So for the next number, so I hope you understood, right? I just mapped it and then calculated it. So for the next number Q is 0x, oh man, 3F 5C2EF4. Okay, they were playing, I guess. Okay, so you just have to put it again here. So it's 0 0 1 1 1 1 1 1 0 1 0 1 1 1 0 0 0 0 1 0 1 1 1 0 1 1 1 1 0 1 0 0. It's always good to know the binaries from 0 to 15. That way you can do it like me only. I remember the binaries, that's why. So 0 is nothing but positive. The next 8 bits, 1 2 3 4 5 6 7 8, this denotes my mantissa, sorry, exponent, and the final thing denotes my mantissa. Okay. Okay. So if you now calculate, this is nothing but, this is positive. So Q is nothing but 1.0 into 2 to the power. What is the exponent here? What is the exponent here? Exponent is 126. So 126 minus 127 multiplied by, oh sorry, it's not 1.0, right? So exponent is this multiplied by 1 point, this entire m. I'll just write it as m. Okay. When you are multiplying these two numbers, this was 1 only, right? So this is nothing but 1 dot m. So it's nothing but, so if you multiply p times q, you get 1 dot m only, right? Minus is there because minus multiplied by positive is minus 2 to the power 4 multiplied by 2 to the power minus 1 by, because this is 2 to the power, sorry 127, sorry 127. So this 2 to the power minus 1 multiplied by 2 to the power 4, this is nothing but minus 1 dot m multiplied by 2 to the power 3. Now if you want to represent this, so sign bit is 1, right? Again, let me write this as full final one. So sign bit is 1. The next 8 bits denote the exponent, so it's a biased exponent. So the biased exponent is 133 plus 127, right? So this is nothing but 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is my exponent, and then the rest becomes my mantissa, right? Mantissa is 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0. So you start from the right, group in fours. Okay, this is C, this is 1, this is 5, this is C, this is 2, this is E, this is F, this is 4. Okay, sorry, this, uh, 1 second, I think I did some mistake somewhere. Okay, so let me write it again. Let me write the thing again. Okay, so no problem. So the sign bit is 1 because it's a positive number. Sorry, negative number. This is the sign bit, right? Then the next 8 bit denote the exponent. So 130 is 1, 0, 0, 0, 0, 1, 0, right? Right. So I think, wait a second. I think I'm, okay, I was missing a 0 because it's 8 bit, no? Okay. Okay, fine. Sorry about that. Okay. Okay, so this is the thing, and then the rest 23 bits denote the mantissa 101. I think I wrote the correct one last time only. Okay, got confused with so many numbers. 1100, right? 0010, triple 10, 4 1s, 0100. So this is 4, this is F, this is E, this is 2. So till here I'm done. This is C, here I'm done. This is 5, here I'm done. This is 1, this is C, C1 5, C2 E4. C15, C2, E4. Option C is the right answer. Okay. Okay, fine. So one thing that you might think is I'll convert this to binary, but if you convert just P, you get 1 times anything is that itself. Okay, last question for that was asked in the GATE exam was on cache memory, right? Okay, fine. An 8-way set associative cache of size, sorry, 64 KB is used in a system with 32-bit address. The address is subdivided into tag, index, and block offset. Number of bits in the tag is what? So let's draw the block diagram. You have a 32-bit address, right? Divided into 3 fields: tag, index, and block offset. Okay? It's a entire thing is 32 bits because it's given that the address is used in a system with a 32-bit address, right? 64 KB is the cache size, right? 64 KB is the cache size. So okay, okay. So see, okay. So this thing, right? Index along with the block offset means there are so many lines or sets in the cache. Each set or each line has this block offset, right? So this is nothing but your cache size. So this is 16 bits. Okay, right? And then the remaining 16 forms your tag. But hold on, hold on. Remaining 16 forms your tag, but it is a k-way set associative cache, which means, okay, let's take a simple example. Let's say you have 1024 lines in your cache. Each line or blocks, okay, let's not confuse between line and block. The same thing, but it's written block offsets. Each has about 64 byte blocks. Okay, so what will be the block size? It will be 6. What will be the line? What will be the number of bits here? 10. So what my cache is now what? 2 to the power 10 blocks, each block having 6 bytes. So that is my cache size. That is given as 64 KB. Here it is, let's say I'm now making it further and saying it is a 8-way set associative cache, which means from 1024, instead of 10 bits, what you have to do is you have to first divide by 8. So it is, sorry, it is so 1024 by 8 is 128, right? So 128, right? So now you need 7 bits for the index, because if it was a direct mapped cache in the earlier scenario, then the index is the block offset, block number, sorry, so it's 10 bits. Since it's a 8-way set associative, index is a set number, which is 7. So you divide that 1024 by 8, you get 128 sets, so 7. So how many bits you went to the tag? You sent 3 bits to the tag, right? Because instead of 10, it's now 7, right? You're sending 3 bits to the tag. So instead of 16, how much it will be? 19 bits. Okay, so that is the right answer. Okay, fine. So this was I wanted to talk about in this lecture, the question solving for computer architecture for the GATE CS 2023 exam. With this, I would like to conclude this lecture. Again, please, if you need more information, contact us at this website. You can email us and call us. You can also write below, comment down below, or like this video, or share this video with your friends who are studying for the GATE exam. like and comment down below. Subscribe to this channel for more such videos, and all the very best to your GATE exam. With this, I would like to conclude this lecture.